Hello and welcome back to the Alteryx Weekly Challenge. Me and Bignell. This is challenge number 140, and it's Prove the Birthday Paradox. The birthday paradox is apparently where you can get a room of people. If you get 23 people into that room, the chances of two of them having the same birthday, I don't mean year, I mean day and month within the year, is 50-50 or 50%. So the challenge here is to prove that out by running a trial 1,000 times on each size group, i.e. 2 to 50. So you can then get an idea of what's the chances for each of those groups of two of them having the same birthday. Okay, so if we go to the challenge, what we see here is there's no input data for this. So they haven't given us a random set of data with 50 or 100 or 1,000 birthdays in it. So we will have to generate that, and we could do it with an iterative macro, but I think we could probably just do it using just generating some rows, quite a few rows, but generating some rows. So we start with the first one, and we want to count. So this is the number of people in the room. So number, what did they call it in? So if we look at so we've got number of people and then chances. So this is what the output that we're looking for is the 2 to 50 and then the probability. Okay, so if we start with number of people, and we'll start with 2, and we'll just use this. So number of 50, and we want to go people, and we want to go up to 50. Okay, and then the iteration is +1 each time. So if we do that, that gives us the iteration. So that's the first one, and that will give us a row count if we run it. Yeah, 2 to 50, 49 rows, which is the row count we want here. So we want to get back to this eventually, this number here. So let's then give each person within here a reference. So what we're trying to do is build up the rows so that we can give a birthday for every person in all the different combinations, and then so let's do another generate row. We add that on there, and then we basically we're going to call this I guess it's kind of like group ID or something. So it really matters, but I'm going to start with 1, and we'll just add that. So group ID, and we want it to be this up to the number of people. Yeah. Okay. And then it's just group ID +1. So add in there. Okay. So that will then generate for every combination. So here we've got 2 people, and it's given us 1, 2, and 3 people, 1, 2, 3, 4 people, 1, 2, 3, 4. Right. So that's given us a row for them, and now we need to actually multiply that because it wants us to do it 1,000 times. So we actually need to multiply that by 1,000, each one of them. So yeah, so we've got to. So we'll call this one. We'll call it trial number. We start 1, we go up to 1,000, and then let's just put in a trial number. So this will generate 1,000 for each one, which gives us like quite a few rows. Yeah, 1.2 million, 1.3 million. So let's now generate a birthday for each of these rows, because this will represent each individual in each trial, for each number of people. So let's do this, and we want to call it birth date, and birth date, Now there's a formula I think we can use. Where is it? Is it in math? Yeah, rand int number. So that will generate a number, and this is the range of the number. So if we just change that to, I guess, an integer, we'll be fine. We run that. Now that should, yeah, give us a day, a day of the year for each of our individuals. There we go. Okay, so now we can see if any of them match on these things. So what we're looking to match on is the trial number and, is that right? I was trying to think. The birth date, I think we want to match on. Yeah, it's the number of people, obviously, grouped by that. It's the trial number, so we group by that, and then the birth date. So we group by the birth date, and then what we can do is count those. Yeah, so if we count, it doesn't really matter which row we choose, but we just want to count the rows for each of those. And if we do that, we should. Okay, now most of them will be. Yeah, there's the odd 2 in here. See here, we've got 2. So we can just now filter onto those that are not 1. So if we do bring in a filter and we do count does not equal 1, and that should give us just those that are, yeah, here we go. So just those that are 2 or more. So we now need to group them. By the trial number and the number of people and the trial. Okay, no, it's not this count here. It's distinct count. I think it's going to be distinct because we've got duplicates in the data, I think. If we look down here, yeah, we've got, like, this one's got, like, so it's distinct count of the trial number. So we do count distinct. That won't not take us over. Shouldn't take us over 1,000 in the trial. Let's have a look. See. Yeah, that's right. Okay, so that's now. So now we can get the probability out. This is the number out, probability number out of 1,000. So we can get it as a percentage or probability by just taking that number and, so what do they call it here? They call it chance of same B day. So chance of same B day. Okay, and that is simply going to be the distinct count divided by 1,000. And that should, if we do this as a double, will do. And then we can just get rid of, if we bring in a select and a browse. So if we just get rid of we don't need this one. Let's see how close we are. We won't get exactly the same number because obviously we're dealing with a random number set here. But that will give us pretty close, I think, to this. Now 23 is over 50%, so 50.2 in here. Actually, it's just under, but so it's 50, so it's pretty close. I'd say actually his was proving that 24 is, you're going to get it. But anyway, so that's it. Now, when I was looking at this, trying to work out how to do this, I noticed this Wikipedia page. telling you about this birthday paradox, this birthday problem, it actually gives you the calculation, basically the calculation here, which is the paradox of probability is basically one, which is, you only have one person and them having the same birthday as themselves is one, and then if you have two, then it's, the chances are that it's not going to happen on 364 days of the year, that or the chances are really small, basically, really high of it not matching, actually, is what is written here. So you take it the other way. So I thought you could, I'm trying to have a go and see if we can just generate that in, or generate this calculation and see how close we are to the results we've got in here. So if we generate, I think we can probably use the same, generate our groups. So generate the 52 to 50 people. Now the formula here is it's basically the number of people minus 1, n minus 1, right? So let's basically, we can just create a column called n minus 1. Now that will give us the be able to let us take that off 365. So it is the number of people minus 1, as simple as that, and that will give us a something we can use. You could write all of this, I think, in one formula, but I'm going to break it out to make it easier to follow, and then, or maybe easier for me to follow. And then the next one is we've got to then work out what that is out of, in this formula. We've got to work out, to get this 363, for example, here. So let's do that, and that's simply if we do this. So do this formula. So we do the top half of the formula, which is 365 minus n minus 1, and then we divide that by 365. Now that should I need to create a new column for this, so I'll call it prob of match. Prob of match, okay, and we'll make that a, it doesn't matter what it is, double would be fine. Okay, so that will, and then what we want to do is, then we want to create a running total. Why isn't it like that? Syntax. I haven't got the minus sign in there. There we go. There we go. That's it. So I might just put this in a little box because that's going to run for a while every time we run it. So what we've got now is the probability of each. You see it goes down, of each kind of combination. Now we need to do that times that times that to give us the build up of the calculation as it is for each of the number of groups. So I think what we can do there is a multi-row formula. Okay, so but first I thought, because you can only select like 0 or closest value for the first one, otherwise it will mess up. So I think we need to put in a value to start with, and we'll just call it running prob of match, and that will simply equal 1 just to get us going, and then in here we can then adjust it, or we can change it. So if we take that running prob of match, now we don't want it, we just want to set it to nearest, so it takes that 1 on the first row and uses that as its first input. And so we want to take, because we've got to take it from the row above, and there isn't one on the first row. So if we take the running prob of match and we times it by the conditional, because if you look at this formula, it's that times that times that times, exactly. So Right, so if we then take that and we times by the conditional on the same row, what's it? No, the probability of match, and then that should give us the rundown. Let's have a look. Yeah, so that's the probability of it not matching. Yeah, so that's the probability of us not matching in the group. So all we have to do, therefore, is kind of so I've got that the wrong way around, but it doesn't really matter. But we can take that and we can do 1 minus that number. So okay, so that will then hopefully browse on the edge give us a similar distribution. There you go. So we've got a similar distribution to this here, and if you go to 23 we're 49. On here go to 23 we've got 50, and then here at 23 we've got 50.7. So, and then it goes all the way, it gets more and more. So that's the maths behind why this works or doesn't work, or the 23 is a match of 50-50. Thanks very much for watching. See you again next time.